Bismillahirrahmanirrahim. So today we are going to discuss the geometric isomerism. Just to remind our previous lectures, the geometric isomerism is actually the subtype of configurational isomerism, and configurational isomerism is the subtype of stereoisomerism. It means that stereoisomerism is basically of two types: the conformational isomerism and the configurational isomerism. The conformational isomerism is due to the free rotation of a sigma bond, while in the configurational isomerism there is no rotation between the sigma bonds, but actually they are the result of permanent structures. So in this case the permanent isomers are formed instead of uh, interconverting forms due to the rotation of a single bond. Now come to the configurational isomerism. The configurational isomerism is again divided into two types. One of them is the geometrical isomers and second one is the optical isomerism. The geometric isomerism is our topic today. Remember that geometric isomerization is the type of isomerization in which the isomers differ in the arrangement of atoms or groups around a double bond. So let's see an example. In this case, the 2-butene, there may exist two forms. One of them is the cis-2-butene and second is the trans-2-butene. In the cis-2-butene, both the methyl groups are at one side of the molecule. Here you can see that the methyl group both are shown at above. If you see that in the three-dimensional molecule, if you rotate the molecule in a manner that both of the methyl group at downward position or at right side or at left side, but how you rotate the molecule, always both of the methyl groups are on the same side. So this type is called cis-2-butene. And in the second form, the trans-2-butene, one of the methyl is at above side and second methyl is at downward position. And in case of the three-dimensional molecule, you rotate it in any direction, you will see that always both of the methyl groups lie at opposite side of the molecules. So this is called trans isomer of the 2-butene. Remember that geometric isomers are caused by restricted rotation around a bond. The double bond which is present in this case restricts the movement of the molecule, and it is quite different from the conformational isomerism where the single bond is present, which is the sigma bond, and it freely rotates to give you various forms of the molecule. As you see in the picture that here this sigma bond, which is a single bond, is rotating, as a result of which different conformers or conformational isomers are being formed, which are named, as we have studied in the previous session, eclipsed, gauge, or partially eclipsed or staggered forms. Here is the chart which shows different conformers at syn position when both are on 0 degree, gauge 60 degree, eclipsed 120 degree, NT when both are at 180 degree, eclipsed 240 degree, and gauge 300 degree. We have studied these in our previous sessions. The double bond actually restricts the movement of uh, the molecule or the bond. This is like the case you may have seen that when you hang a picture or a nameplate using a single nail like this one is allowed to free, it falls just like it is falling in this picture. But when this is hanged with two nails, the nails in this case restricts the falling of the nameplate. Same is the case with double bond. The double bond restricts the falling or movement of the molecule, but the single bond, which is the sigma bond, can rotate freely. And single bond rotation forms the conformational isomerism, while double bond gives the permanent structure. And in this case, this is called uh, geometric isomerism. Now discuss about the how they are named, the geometric isomers. The old method to name them is putting a prefix cis or trans before the name. Just we are using in these examples cis-2-butene and trans-2-butene. Actually, cis means that both groups are on the same side of the double bond, and trans means that the groups are on the opposite side of the double bond, or they are at across positions. This is the across position, and in this case in cis form they are on the same side. But this creates some problems too, which we are going to discuss uh, in a few seconds. But first of all, let's see how these isomers, the cis and trans isomers, are different from each other. For example, this animation shows that in this case the cis and the trans isomers are different from each other. For example, it is the cis isomer of 2-butene, and this is the trans isomer of 2-butene. You may call the green colored atom the methyl groups if you are thinking that this is the butene, or in other cases you can call this green colored uh, ball as a chlorine or bromine or any other atom which is single valent and is bonded to carbon directly. You see that when animation starts and the trans isomer is put over the cis isomer, they are non-superimposable. They do not cover completely each other, and even at other angle when they are rotated, they are still not superimposable, do not cover each of them The molecules do not cover completely each other. It means that both are different in their characters. And same is the case when you consider this molecule and see the electron cloud around different atoms. Here the blue dots, you can see in the picture that around each atom there is a blue cloud which indicates the electron density around each of the atoms. And in this case, the electron density is quite different from this, this isomer. It means that the electrostatic behavior of both will be different. That's why they show different characters. We also discuss this in some of the different properties, physical as well as the chemical, to show that they are different from each other. For example, this table shows that melting point and boiling point of different isomers of cis and trans series are different. For example, cis butene has the melting point minus 139 degrees Celsius and its boiling point is 4 degrees Celsius, while the trans 2-butene or butene has melting point minus 106, which is very different from the melting point of cis isomer, and its boiling point is plus 1. In case of cis 1,2-dichloroethene, the melting point is minus 80 degrees centigrade, while its trans isomer has the melting point minus 50 degrees Celsius, while the boiling point of cis isomer is plus 60 and of trans isomer is 48. So there is a great difference between each isomer. In case of cis pent-2-ene, the melting point is minus 151 and its trans isomer has the melting point minus 140 degrees Celsius, although the boiling point is have a very little difference, but there is a difference in both of the isomers. This table shows that there is clearly very different melting point and boiling point between the cis and trans isomers. Now take an example of a chemical reaction. For example, in cis butene dioic acid, where both of the hydroxyl group are present on the same side and its trans isomer has, you see that carboxyl group and the carboxyl group, they are at different side of the molecule. So this is the cis isomer and this one is the trans isomer. This has the melting point 140 degrees centigrade and the trans isomer has the melting point 300 degrees centigrade, and there is a great difference between each of them. Now see their chemical behavior. The cis isomer undergoes dehydration easily and is converted into cyclic anhydride. This is the cyclic anhydride formed by the dehydration of cis isomer. But the trans isomer does not go under dehydration under the same conditions. It does not shows this chemical reaction. It means that they are chemically different too. The geometric isomerism can also arise in the compound in the cyclic compounds and where no double bond is present. For example, in the case cis 1,2-dichlorocyclobutane and a trans 1,2-dichlorocyclobutane. You see that this is the cyclobutane and has two chlorine atoms at adjacent atoms. When both of the chlorine atoms are on the same side, the compound is cis 1,2-dichlorocyclobutane, and in case when one of the chlorine is at upward and second one is at downward or forward and backward positions, just like you see in the three-dimensional structure of the molecule. You see that this is the trans isomer and this one is the cis isomer. Structure of both is different, and there is also no double bond. You see, there is no double bond in the molecule. So, and this is a permanent structure, not a although there is sigma bond or single bonds, but they are non-rotatable. So when they are non-rotatable, it means that they cannot interconvert between each forms, and so these are the permanent structures and the permanent forms of cis and a trans 1,2-dichlorobutane. So they are also a geometric isomerism. Moreover, the geometric isomerism can also occur in the compounds which have the double bond, like carbon and nitrogen double bond or nitrogen and nitrogen double bond. The geometric isomerism can also exist in such compounds. Hope you have a good understanding about the geometric isomerism now. Now see how they are named, which we left that old method of the name was cis and trans. Cis when both groups are on the same side, and trans when both groups are on trans positions or across positions. But we have seen that we have told you that uh, this also creates some problems. So to resolve these problems, we have another uh, substituted system for naming them. Normally cis and trans are used. Cis means on the same side and trans means on the opposite side. For example, in this case this works well when cis 2-butene and trans 2-butene are considered. But in the case when different groups are present, for example, here is a case, a double bond. At upward position there is a chlorine and the second carbon contains fluorine, and downside there are both the methyl groups. Chlorine or even the amino groups are present in the second case, but how they are named, this is a cis or this is a trans. If you take the methyl, it could be cis, but when you consider the chlorine and fluorine, it could not be the case. So to resolve such issues, a modified system of naming called Cahn Ingold Prelog system, notational system, is used, which provides absolute configuration at the stereogenic center. I have corrected the spelling. Cahn Ingold Prelog notational system. Prelog notational system. Now, to understand this system, how this works, it is quite easy. Just remember some of the rules. First of the step to name such compounds or geometric isomerism is the naming of molecule by simple IUPAC method. That is, first of all, give the name, the simple IUPAC name to the compound, and the stereochemistry you will see be discussed in later. So, after giving the simple IUPAC name, assign high or low priorities to the two substituents or all the substituents attached to the carbon. Remember, the priority is given to that atom or group having greater atomic number. The atom which has greater atomic number has a greater priority in the series. And if there is a tie at any substituent, means they have the same atom with the same atomic number, then look at the second and then third member of the series, member in the chain, until a difference is found. The second step or second rule is the determine whether both high priority substituents are on the same side of an imaginary line running through the double bond or on the opposite side. Number third step is the assign configuration Z to the isomer which has both priority substituent on the same side. Remember that Z is a German word, zusammen, which means together. And assign configuration E to the isomer which has both priority substituent on the opposite side. E is a Latin word derived from the Latin word intigen, which means across. This is further explained in the figure. You see that this is a case where a molecule, carbon, and a carbon at this joint is also there. The above side carbon has methyl group and a hydrogen, and the down carbon is a methyl and an ethyl substituents. The simple name for this compound is 2-methyl 2-pentene. 1, 2, 3, 4, 5 means that it is a pentene. Double bond is at position number 2, so it is 2-pentene. The methyl is at carbon number 3. At carbon number 3. So the IUPAC name for this compound is 3-methyl 2-pentene. 3-methyl 2-pentene. In both of the isomers, the same is the situation. Now we have to assign the stereochemistry of the compound. So all of the groups in this case are carbon. There is a tie. To solve this problem, look for the next neighbor of the carbon. Hence, this methyl is having high priority than hydrogen, but in this case there is a carbon which is further jointed with hydrogens, and in this case there is a carbon, two of the sides are covered by hydrogen, and third side another methyl group is present, means that this is bonded to another carbon. So this is high priority over this methyl group. So this one has a high priority and this one also has a high priority. In this case both high priority are across, and in this case this type of isomer, the high priority methyl is at the same side where this high priority group lies. So we will name the compound in which the both of the high priority groups are across to each other as E isomer. So this is the E 3-methyl 2-pentene, and this one is Z 3-methyl 2-pentene, in which both the high priority groups are on the same side. This is the imaginary line which bifurcates the molecule. So Z means both of the high priority groups are on the same side, and E means that both of the high priority components or atoms or groups are on the different sides. So this naming method absolutely will resolve the issues we have discussed above. For example, in this case, you see that carbon is joined with chlorine and a carbon, and this is fluorine and a carbon. In this case, chlorine has atomic number 17, fluorine has atomic number 9. So obviously chlorine 9, and in this case carbon, which has atomic number 6, carbon number 6, both have the 6. High priority is 17 and 9. Both are on same side. So it's another isomer in which fluorine is at downward position. In this case, both high priority groups are on the same side. So this is Z or Z isomer, and if fluorine is present at downward position and methyl at upward position, then the isomers will be E type or E isomer of the compound series. Hope now you will have understand how to name the geometric isomers and what is Cahn Ingold Prelog notation, and even what is the geometric isomerism. We will continue our stereochemistry topic in our coming lectures. Thank you.